All right, so in this question from the old Physics B test, we're going to use some concepts that aren't completely on the Physics 1 test, but I think it's still good practice, which is why I'm keeping it. And it's nothing that is beyond you guys, but you don't get the equation sheet reference. So you might, I think it's realistically it could ask you to derive some of this. So keep in mind that this may be a bit more than you would ever have to do on the AP test now, but conceptually you should be able to explain what I'm calculating even if you can't get the exact equations for all of it. So with that being said, we're dealing here with a setup where we have speakers and two different points a distance away, and we're having to figure out some information about what the sound intensity or the loudness is like. Right, so our diagram looks kind of like this. And point right through the center. This 0.75 meters. This is 5 meters. We have point P. We have point Q. And this is some distance y. Okay, we're also told that V sound is 343 meters per second, and we're told that the frequency is 2500 hertz. Okay, so the first part is definitely something that you can do. We are told the speed and the frequency, and we want to know the wavelength. So we use that relationship and we solve for the wavelength. So 343 over 2500. And if you plug that in, you get 0.137 meters. Right, since the velocity is in meters per second, the wavelength will be in meters. So this next part is the part that we've covered the equations in class conceptually, but we may not have exactly the availability of the equations on the AP test. So for part B conceptually, we know that the concept of what we're trying to do, this idea of the path length difference, must equal half a wavelength. Because half a wavelength, right, that difference means that they're going to destructively interfere. When one is at a crest, the other will be a trough, and so on. And so if they travel differing amounts of distance to create that difference, then we know we get dark, like the low amount of sound, right? And so all we're doing conceptually is we're trying to calculate this thing. Right, this is like R1. That was terrible. Let's see if I can get that to actually work. There. And this is like R2. And so, let's see. Right, delta R is just R2 minus R1. I mean, the difference between those two lines. And so, in general, this can be kind of a tricky calculation, as you can see. But if we notice some triangle properties, then we can make our math a little bit easier. But in this case, I'm not going to do that. I'm just going to do the math right out. This is really a geometry problem. So make sure you're kind of comfortable with that. So here's what we're going to do. What we need is a way to write this R2 value in terms of lengths we do know. Right? That's the idea. And so I'm going to start with, actually I'm going to get rid of some of this in blue because I need that color. Right? We know that this is just going to be R2 minus R1. Oops, 1. Right, okay, so I'm going to use blue to draw out sort of the triangle to calculate R2, right? R2 is part of a triangle that looks like this, right? Where this side is the 5 meters, and this side is two things. It's 0.75 over 2, that's this bit, plus y, that's that bit. And so we can write R2 equals, using the Pythagorean theorem, 5 squared plus 0.75 over 2 plus y squared square root. Right? Okay. We're going to do the same thing for the closer speaker. Right, we have this distance and the same 5 meters distance. So we can also write R1. Now, R1's a little trickier, right? Here, this is that same 0.75 over 2, and then this is sort of what's left over. So this one's a little bit uglier. 5 squared plus y, the total thing, minus that little bit. Right? So geometrically, I've now written it. And we know what the wavelength is, right? This just goes in there. So now I have an equation that technically can be solved. Again, algebraically, it's hideous, fine, but let's go write it out and we'll look at it. So y plus 0.75 over 2 squared plus 5 squared square root, oops, right, that's R2 minus y minus 0.75 over 2 squared plus 5 squared. And that equals lambda over 2, because that's when it's quiet. Right? So, if you can get to this point, you understand the concept of the physics, and you've been able to successfully do the geometry. I'm not going to expect you to do the algebra to actually solve this for y. You kind of need to do it with a calculator because it's really ugly, right? If you were going to solve this, you'd have to square both sides, do some distributing. It would be ugly. But the point is, it can be algebraically solved. I don't expect you to be able to do that. Again, I expect you to be able to get to this point, right? To be able to set up what that idea of the path length difference means and what you're looking to create, the half wavelength difference to make it quiet. So, with that being said, here's what the answer is. If you work it all out very carefully, you will solve for y equals 0.460 meters, right? And so that's the answer to part B. Again, I don't expect you to get that, but you should be able to set up the concepts. Okay? So that's part B. Part B is the part that is the most different from what I would expect the current AP test to do. So that's the answer. Part C. We're asked to identify another location on that same line, right? This line here, that would be really quiet as well. The simple there are a lot of answers. First of all, to this, there's not just one answer. But the simplest answer is that you want to go a distance y in the other direction, right? It's symmetric about that middle point. So there's a point right up here, Q prime, that's exactly 0.460 meters above point P instead of below. That's one. The other option would be to say, well, we know minima happen every extra half wavelength. So if we instead change this, right, this condition right here to be this thing plus a full wavelength. Oops, let me actually write that a bit more neatly. That's still ugly. right? If we change this to be what it was before, plus another wavelength, right? So it repeats once and then goes an extra half wavelength, and we solve this, right? Solve this new ugly equation, which is the same idea as before. We'll get a new sort of y prime value equals something. Whatever that is, that's also a distance when it's going to be really quiet, right? So that turns out that would be a distance, right, 2y more, right? I could also put point q prime down there, which is now a distance, right, 3y from the center. That would also work. I think the simplest answer is the mirrored one. That's the one I expect you to recognize, that you're going to have a silent spot on both sides of the center that are sort of symmetric. Okay. So that one I expect you to be able to do for sure. Part D, we're changing a couple things, right? And I definitely expect you to be able to do D part 2. D part 1's a little trickier, but you should still be able to do it. So let's go back to this equation, right? If the two speakers are moved closer together, this term here and this term here are a bit different, right? Namely, they're smaller. Right? Instead of being 0.75 over 2, maybe it's like 0.1 over 2. It's a smaller number. So as that gets smaller, there's a couple different ways you can prove it. You could just recalculate this whole equation by picking a number that's smaller than 0.75 to plug in there. Or you could notice that as d gets smaller, y is going to get larger. Again, this is one that I don't expect you to recognize in full because the derivation that shows that very clearly is not part of Physics 1 anymore, but you should be able to recognize sort of what you're changing, right? If we move the speakers close together, we're changing that thing circled in red. And so if D goes down, actually that's not right, I just I didn't use that label yet. So if we change from 0.75 to like 0.1 separation, then we're going to find that y goes up. Right? Again, you can just calculate that straight out. It doesn't change the whole process. The key is to recognize what gets changed. Part B is a little bit more straightforward. Right? This one I expect you to be, or D part 2, this one I expect you to be able to do. If the frequency goes up, so if the frequency goes up, the speed of sound has not changed, so we know that the wavelength goes down, right? If the wavelength goes down, that means we're changing this term over here. So we have that huge collection of stuff equals now a smaller number. And we can see that y is going to be directly proportional to the wavelength. So y must go down, right? If this side of the equation is smaller, this side of the equation must also get smaller, which means y must go down. So that's our final answer for that. Okay? Again, looking at this problem in total, you should be able to do part A. You should be able to set up and understand what's happening with part B. You should be able to draw, even if you can't calculate all the other spots, you should be able to show me generally where another thing is in part C. And in part D, you should definitely be able to do part 2, and maybe if you're really good at algebra, do part 1. So it's kind of good practice with some geometry stuff.